Morning, everyone. Sorry I'm a little late here. Morning, everyone. Morning, everyone. This is really happening. This is really happening. Nobody's working, nobody's happy. Take the money on, take the money on, take the Morning, everyone. Come on in. I wrote the 10th, right? But it's the 11th. Or did I write 11? What did I write? I don't even know what I wrote. I might have written 9. Yeah, it is the 11th. I'm 2 days behind, apparently. I wrote that. Sorry about that. How are we doing? Yeah, my mistake. Sorry about that. We are the 11th. Let's go back to that, Matthew.
Partial fraction decomposition. What does it say? It says that if you have a rational function, p of x over q of x, where p and q are polynomials, and the degree of p is strictly less than the degree of q, then you can break this up into a bunch of smaller fractions, partial fractions. By decomposing q into a product of irreducible polynomials, so decompose q into a product of irreducible polynomials. What does this look like? q1 to some power, q2 to some power, and so on, qn to some power, where the qi are irreducible. Then p over q has the form p11 over q1, p12 over q1 squared, and so on, p1 k1 over q1 k1, all the way to qn1 pn1 over qn plus pn2 over qn squared, and so on, all the way to pn to the kn over qn to the kn, where the pi's are polynomials of degree less than qi. That's what partial fraction decomposition says. We're not going to prove this. First of all, we don't even understand what this means. So, no point in proving that. Let's instead get an understanding of this via some examples. And the first example I suggested last time, let's look that over. Let me make an addition to this theorem here. The Pij are unique. In other words, if you have a partial fraction decomposition, then you have the partial fraction decomposition. Let's illustrate with an example. So last time we considered this one. We didn't completely do it, so let's do it now. Well, actually, the question is asking us to write out the form, do not solve. But we're going to do more than that. We're actually going to solve it. So, you have this. And even though there's no integral here, right, all it's asking us is to find the partial fraction decomposition, you can very well imagine a question on the midterm which asks you to integrate this. How would you do that? Well, I mean, it's not obvious how you would tackle this, but if you factor out an x squared, you have this. And if you want, let's rewrite x squared as x all squared. Now, before we continue, I should mention that, we reviewed on Tuesday the idea of irreducible polynomials, and we saw that there are only two types of irreducible polynomials. Polynomials of degree 1 or polynomials of degree 2 with no real roots. Here, x is a polynomial of degree 1, and x squared plus 1 is a polynomial of degree 2, but you can verify that it has no real roots. So both of these are irreducible polynomials. What partial fraction decomposition says, what this big statement here says, is concentrate on the first irreducible polynomial. Why don't we keep x squared as it is, since it's irreducible already? It is not. X squared is not irreducible. X squared, so convince yourselves that x squared is not irreducible. Because it's a polynomial of degree 2, but it has roots. It has real roots, namely 0. Exactly. 0 is a root. No. Degree 2 polynomials are not irreducible in general. Right? I mean, if you have x squared plus 7x plus 12, this factors as x plus 3, x plus 4. So this is not irreducible. It factors. X squared is not irreducible because it factors as x times x. Polynomials of lesser degree. Very well. So there we go. We have decomposed this as a product of irreducible polynomials. The x, we have two of them. The x squared plus 1, we have 1. Right? So this is what we have done. We have decomposed the denominator as a product of powers of irreducible polynomials. Partial fraction decomposition says concentrate on the first irreducible polynomial. So polynomial of degree 1. So we're going to search for a polynomial of lesser degree. Less than 1. The only possibility is 0. So a real number over x plus another polynomial of degree 0 over x squared, and you continue until you've exhausted the power, right? That's what's happening here. Q1 squared, Q1 cubed, all the way to Q1 to the K1. Once we've dealt with first irreducible, move on to the next one. Next one is x squared plus 1, which is a polynomial, an irreducible polynomial degree 2. So we search for a polynomial degree 1 on top, right? Degree of the numerator is less than the degree of the denominator. So degree 2, we search for degree 1, cx plus d over x squared plus 1. And then you would have said ex plus f over x squared plus 1 squared, and so on until you've exhausted the power. But the power was just 1 here. So It's already exhausted. You would have moved on to the next irreducible, but there are no more. So that's it. The suggestion, or what partial fraction decomposition says, is that there exists A, B, C, and D for which this is equal to that. Let's solve. Let's solve and convince ourselves. Let's put everything back over common denominator. The common denominator is the denominator we started out with. So I need an x and an x squared plus 1. For the b, I need an x squared plus 1. And for the cx plus d, I need an x squared. Right, we're putting everything over common denominator. For the denominator with degree 2, can the numerator be a constant? It could happen. It could happen that the denominator is a constant, but we don't know. This says the degree is less, strictly less than the degree of the irreducible. So this has degree 2. This could have degree 1, or it could have degree 0. It could turn out that C is 0. But we don't know that a priori. We have to do the work. Exactly, Ashlyn. If x squared plus 1 was to the power 2, you would then have an ex plus f over x squared plus 1 all squared. Absolutely. If you put everything back over common denominator, you have this. So this has to be equal to that. And you see that the denominators are the same. So the numerators must be the same. Right? If you multiply the whole equation by x to the 4 plus x squared, everything's going to cancel, and you'll be left with just the numerators being equal. Is adding the d mandatory? Absolutely. Right? Don't start with a preconceived notion of what the polynomial has to be. Right? We're looking for, all we know is that the polynomial is of degree less than the denominator. So this is an irreducible of degree 2. This could be degree 1 or degree 0. We don't know. We don't know the form. We don't know anything. So this is what any polynomial of degree less than 2 looks like. If C is 0, you get a polynomial of degree 0. If C is not 0, you get a polynomial of degree 1, even though D may or may not be 0. That's exactly what we're saying. Irreducible of degree 1, polynomial of degree 0. Irreducible of degree 2, polynomial of degree 1. It's the irreducible that's important. Irreducible of degree 1, polynomial of degree 0. The irreducible here is still degree 1. It's still x. It's just that you have 2 of them. Right? Here, the Pij, the degree of Pij does not depend on j. It just depends on the irreducible. Expand everything. And now let's group the powers of x together. Is that correct? Yep, exactly. No. If this had been squared, we would have had an ex plus f over x squared plus 1 all squared. You were missing the square there in the denominator. All right. Everybody with us here? And now, take a step back, and what are we looking at? On the left-hand side, you have a big polynomial. From here to there, common denominator. I'm still confused why it is b but not bx plus c. It's the irreducible that's important. The irreducible is x, which has degree 1. So we search for a degree less than 1 on top. The irreducible is still x. It's just that we have 2 of them. Irreducible of degree 1, so degree 0 on top. If the functions were reducible, would the numerators all be constant? Who knows what happens if we have reducible stuff. Let's not even consider that, because we want irreducible. So the Ashlyn is suggesting the top polynomial is based off whatever the degree of x is in the denominator. No. The degree of the irreducible in the denominator. So why is it cx but not ax and bx? Well, I mean, here the irreducible is degree 2. So we search for a polynomial of degree less than 2 on top. Cx plus d. Right? It has to do with the degree of the irreducible polynomial. So here, on the left-hand side, you have this big polynomial. But on the right-hand side, you also have a polynomial. Right? 1 plus 0x plus 0x squared plus 0x cubed. And now the only way 2 polynomials can be the same is if their corresponding coefficients are the same. Coefficient of x cubed on the left is a plus c. Coefficient of x cubed on the right, you don't have an x cubed. The coefficient is 0. Coefficient of x squared on the left. Coefficient of x squared on the right. Again, there is no x squared. It's 0. Coefficient of x on the left. Coefficient of x on the right. There is no x. Constant on the left. Constant on the right. Thank you for pointing that out. Web work 2 and 3 have been released. Have a look at those. So you see what's going to happen in general. you have 4 equations, 4 unknowns. This is from the numerator, right? We have this is equal to this. So multiply both sides by the denominator to get rid of it. And the numerators must be equal. Bahar, all I'm suggesting is that we equate the coefficients. Coefficient of x cubed on the left is a plus c. Coefficient of x cubed on the right, there is no x cubed, coefficient is 0. And so on for the other powers. So in general, 4 equations, 4 unknowns. Will these problems always allow for the unknown coefficients to be found? Yes. That's what partial fraction decomposition guarantees. So 4 equations, 4 unknowns, you know what to do. For those of you who have done 133 or are doing it now, you can use matrices. How do you know a is equal to 0? A is the coefficient of x. There is no x. 0x. How do we know that equation is equal to 1? Does it always? No. Constant on the left, constant on the right. So, again, you can use matrices to solve. Here, there's no need. You already have A. And so C has to be 0 as well. And if B is 1, D has to be -1. Of course, you don't need matrices. This is a trivial example. But these get complicated and long. And as you know, matrices are the fastest way to solve systems of equations. So what are we saying here? We're saying 1 over x to the 4 plus x squared is equal to a is 0, so 0 over x, let's forget that. B over x squared, so that's 1 over x squared, plus cx plus d. C we found to be 0, and d is -1. Well, Matthew, you know that you don't need matrices. This is just a system of equations, so you're going to isolate for one variable, plug it in, and blah, blah, blah. It's all good. Right, so here it is. We're saying that this is equal to that. I mean, it's obvious once we've written it out, right? If you put everything back over a common denominator, x squared plus 1 minus x squared I mean, it's trivial. Yeah, exactly. We're doing everything we can to postpone the integration, right? This, which would have seemed like a very difficult integral, if you break it up using partial fractions, suddenly it's trivial. Suddenly it's trivial. Antiderivative of this, -1 over x. Antiderivative of this, arctan x, and you're done. Why the minus? You tell me. yeah, of course, we'll do several other examples. Between the fractions, the line is between the fractions here? Is that what you're, exactly, d is -1 and c is 0. C is 0, D is -1. So, I mean, I'm looking at this business right here. Right? All I'm doing is I'm evaluating what this is. A is 0, B is 1, C is 0, D is -1. So what's the purpose of the other stuff? I don't know what other stuff you're referring to. I mean, the question wasn't even an integral, right? It was just decomposing a function into partial fraction. And that's exactly the question here. But I'm suggesting if the question was the integral, how do you integrate this? Who knows? But if you split it up using partial fractions, then you see the light at the end of the tunnel. And all we did to do that was a bit of algebra. So that's the beauty. We trade some difficult integration, perhaps, for easy algebra. Can we just find what it's equal to without decomposing? Well, I mean, this was easy enough. You might have been able to read it off. And, you know, I mean, once you become good at partial fraction decomposition, you'll see some answers. But, I mean, right away, without doing any work here, I don't know what that is. Here, the question is just asking us for the form of the partial fraction decomposition. It's not asking us to solve. So let's decompose this using partial fraction decomposition. You know, since it is probably easy enough, maybe we'll solve here as well. How does that decompose? Decompose, factor the denominator into a product of irreducible polynomials. Any tips for when to use this technique over integration by parts? Rational functions. If you've got a rational function, I don't know. It seems that, you know, integration by parts here wouldn't be applicable, really. No complex. Thank you, Bahar. This factors as x plus 1, x minus 1, x squared plus 1. Does everybody see that? Right, Sophia did it as x squared plus 1 times x squared minus 1, an excellent start. Why don't we, in case you didn't realize that. Sophia is suggesting x minus 1 times x squared plus 1. This is irreducible already, so an excellent start, but this is not. This is not irreducible, right? This factors a bit more as x minus 1, x plus 1. Yeah, of course, everything goes back to practice. So we've decomposed the denominator into a product of irreducible polynomials. Partial fraction decomposition says concentration of the first irreducible, x minus 1, which is degree 1. So we search for degree 0 on top. And you continue until you've exhausted the power. Well, it was power 1 is already exhausted. Move on to the next one. X plus 1 is degree 1. So we search for degree 0 on top. And you continue until you've exhausted the power, already exhausted. Move on to the next irreducible. Irreducible degree 2. So we search for degree 1 on top. And you continue until you've exhausted the power. Again, power 1. We're done. There it is. That's the form. We don't need to multiply by 5. That's the form the partial fraction decomposition takes. Partial fraction decomposition guarantees there exist A, B, C, and D real numbers for which this is true, for which this is equal to that. The question is that would ask us, in this particular case, the question asks us only for this. So we would stop there. Why don't we write a constant for the first two? I mean, I claim we do have that. Right, so again, the question, as it's stated in the book, this is the answer they're looking for. We're going to take it a step further for practice, and we're going to actually solve for A, B, C, D. Sophia is asking if the denominator was degree 4, then the numerator would look like ex cubed plus fx squared plus gx plus h. Somebody want to answer that? Is that correct? In the meantime, we're going to put everything back over common denominator. Anybody want to tackle Sophia's question? Exactly. The answer is no, because polynomials of degree 4 are not irreducible. The only irreducible polynomials are degree 1 or degree 2 with no real roots. You're never going to have a polynomial degree 4. Let's put everything back over a common denominator. A times x plus 1 times x squared plus 1. B times x minus 1, x squared plus 1. And cx plus d times x plus 1, x minus 1. I think we've answered that question. What if we have an irreducible polynomial degree 4? Exactly. As Rima suggests, the idea is to factor your denominator until you only have irreducible polynomials. So this is equal to that. The denominators are the same, so the numerators have to be the same. So the numerator here is equal to the numerator there, which was 5. So power 2 is never going to be in the numerator. That's right. So only polynomials of degree 1 or 0. Last time we expanded the left-hand side, grouped the powers together, and equated the coefficients. I mean, I've rubbed it off now, but that's what we did. And we got 4 equations for unknowns. You can do the same here, and you'll get exactly that. But sometimes there are some tricks. Sometimes you can get away without doing that, and exactly just plug in some good values. Rima doesn't see how we got the 5 on the other side. We're equating the numerators, right? This is equal to that. The denominators are the same, so the numerators have to be the same. Numerator was 5 here. There it is. So instead of multiplying and grouping the powers of x, we could choose good values of x. If x is 1, observe what happens. If x is 1, this is 0, so that's gone. And this is 0, so that's gone as well. So if x is 1, we get a times 2 is equal to 5. So immediately a is 5 over 4. Matthew, I'm not sure what you're doing there. Not sure what you're doing. I'm suggesting that if you plug in x equals 1, this business disappears and this business disappears. So you can solve for a immediately. A is not equal to 1. A is equal to 5 over 4. Similarly, if you plug in x equals negative 1, this is going to be 0, so that disappears. And if x is negative 1, this is 0, so that disappears as well. So we're just left with the b business. B times negative 2 times 2 is equal to 5. So it's easily seen that b is negative 5 over 4. I'm just saying you may want to plug in good values of x. And 1 is a good value because it gets rid of a lot of stuff. Negative 1 is a good value because it gets rid of a lot of stuff. Maybe we want to plug in 0 because it'll get rid of the c. X can be anything, exactly, right? Because what you have here is one polynomial equal to another polynomial. So these have to be the same for any value of x. So are both a and b used or just one? In fact, a, b, c, and d are all used. We need all of them. If x is 0, what happens? Here we get a. Here we get minus b. If x is 0, that's gone. And we have minus d is equal to 5. But we just found a and b. So that's 10 over 4 minus d is equal to 5. If you interchange, d is easily seen to be minus 10 over 4. 4 minus 5 over 2. You can plug in a and b to find c and d. If this is what you mean, then yes. And then any other value of x, right? I think we've exhausted the good values. But any other value will give us one last equation, letting us solve for D. So I don't know if you want to plug in. Shall we say x is 2? If x is 2, this is 3, this is 5. So a times 3 times 5 plus b times 1 times 5. And 2c plus d times 3 is equal to 5. But we know a, b, and d. So we can plug those in. A is 5/4. B is minus 5/4. D we said was minus 5/2. Maybe we want to multiply by 4 to get rid of the denominators there. I'm just saying, you know, whatever you want to do. So that's 25 times 3, that's 75, minus 25, plus 8c minus 10, times 3 is equal to 20. So that's 50 minus 30 is 20. So clearly C is 0. All of that for 0. Yeah, exactly. Any value of x. Since you already know a, b, and d, all you need, isn't it 6c? Yeah, fine. What I was doing was multiplying by 4 to get rid of the... Look, if you're not a fan of this choosing x values, do it the other way. Do it the other way. Multiply this out, group the powers of x cubed, group the coefficients of x squared, group the coefficients of x, group the constants, and just equate like we did before. All I'm suggesting is that this is a different approach that may sometimes be faster. Not always, but sometimes. Let's try another one. Let's try another one where now we will not solve. I just decided to multiply by 4 to get rid of the fractions. Nobody likes to work with fractions. If you multiply both sides by 4, no more denominator. All right, Here, again, the question is, are we done with our last problem? We are. We found A, B, C, D. The question wasn't asking us to integrate. In fact, we could have stopped a lot earlier. The question was actually asking us not to solve for the constants, but just give the form of the decomposition. This is what we're going to do here. Here we're just going to give the form of the decomposition. We're not actually going to solve. What's the first thing we need to do? The question did not ask for the integral. Right, again, here the question does not ask for the integral, but just the partial fraction decomposition. And exactly right, I mean, the first thing we need to do is decompose the denominator into a product of irreducible factors. X squared minus 1 is not irreducible, right? And this is a difference of squares. This is easy to factor. And here, x cubed minus 1 is a polynomial of degree 3. So you know that it's not irreducible. How does this factor? I mean, who knows? But we do spot a root immediately. X equals 1 is a root of this. So x minus 1 must be a factor. So we can do some long division. Right? I don't expect you to know how this factors, because I don't know how that factors. But I can spot a root, and I can do some long division. What must I multiply to x to get an x cubed? The answer is x squared. This minus this is 0. This minus this is x squared. Bring down the next term and repeat. What must we multiply to x to get an x squared? The answer is x. X squared minus x. And subtract. This minus this is 0. This minus this is x. Bring down the minus 1 and repeat. What must I multiply to x to get an x? The answer is x. And the answer is 1. And we get a remainder of 0 exactly as expected. So this factors as x minus 1, x squared plus x plus 1. And this factors as x minus 1, x plus 1. So you see that these three polynomials of degree 1 are all irreducible. It is a difference of cubes, but nobody knows what that is. So we took a moment to factor it using long division. Right? These three are polynomials of degree 1, so these are irreducible. What about this one? Is this irreducible? It's a polynomial of degree 2. So it may or may not be. How do we get x minus 1? We notice that 1 was a root. If x is 1, you get 0 here. 1 is a root, so x minus 1 must be a factor. Is x squared plus x plus 1 irreducible? That's the question. And to answer that, we're going to find the roots. If there are no real roots, then it is irreducible, right? Because it's a polynomial of degree 2. Using the quadratic formula, negative b plus or minus square root of b squared minus 4ac over 2a. And there you go. Square root of negative, no real roots. Thus, it's irreducible. If the numerator was x squared plus x plus 1, they could cancel out, absolutely. Absolutely. Before we continue on, let me point out here that originally, we didn't bother with anything yet, but let me ask you this. The degree of the numerator, right? The first thing we should do is look at the degree of the numerator, which is 4. And if you multiply this out, you would have a polynomial in the denominator of degree 5, right? One of the assumptions in partial fraction decomposition is that you started out with a numerator of lesser degree. So even though we haven't encountered that issue yet, we really need to check. We have to start with a numerator of smaller degree. So what are we saying? X to the 4 plus x plus 1 over x plus 1, x minus 1 squared, and x squared plus x plus 1. We have now decomposed this into a product of irreducible polynomials. And Matthew asks the obvious question, what do you do if the numerator has greater than or equal, right, because equal is also an issue, degree with the denominator? Long division. Long division is what you start off with. You do some long division, and you will end up with some polynomial plus a remainder over the divisor where the remainder has lesser degree. And then you can apply partial fractions to that remainder business. We'll see an example, I'm quite sure. This is still the same section. I don't know that it's 7.3. I want to say 7.4. Why you got the last step on the left? Well, I mean, we have it here, right? I'm just rewriting it over there. I'm just rewriting it over there, combining the two x minus 1s. Right? We have an x minus, we have two of them represented by the square here. So we've decomposed it into a product of irreducible polynomials. Now let's apply partial fraction decomposition. This is an irreducible polynomial degree 1. I mean, it is absolutely necessary to combine. Yes. Absolutely necessary, otherwise you'll get a wrong answer. So irreducible polynomial degree 1. So we search for polynomial degree 0 on top. And you continue until you've exhausted the power. It's already exhausted. Irreducible polynomial degree 1. So we search for polynomial degree 0 on top. And you continue until you've exhausted the power. Well, at 2, the power is exhausted. Move on to the next irreducible polynomial, polynomial degree 2. So search for a polynomial degree 1 on top, dx plus e over x squared plus x plus 1. We would continue until the power is exhausted, but it already is. If you hadn't combined the x minus 1s together, you might have been tempted to say c over x minus 1 plus d over x minus 1. But that's not the same thing as something over x minus 1 squared. It would have given you the wrong answer. There it is. They're not asking us to solve here. In fact, they're telling us to stop right here. But if this was a different question, it would put everything over a common denominator. Solve for A, B, C, D, E. 5 equations, 5 unknowns. The common denominator will give us the same thing as above, absolutely, convince yourselves. The common denominator, the smallest common denominator is exactly what we have up there. Right, what am I missing? I've got the x plus 1, so I'm missing all of this. B, I've got one of the x minus 1s, so I'm missing this. I'm missing an x minus 1, and I'm missing this. For the C, I've got the x minus 1 squared, but I'm missing the other two. And the dx plus E. I've got this, but I'm missing the rest. X plus 1, x minus 1 squared. That should be right here. Smallest common denominator, Harry, smallest. So now that you have the same denominators, you can equate the numerators. Multiply this whole business out, and equate the coefficients. You'll get 5 equations, 5 unknowns that you can solve using matrices or otherwise. Consider this. 1 over a plus 1 over a squared. How do we add these? We put everything over a common denominator. Some of you want to say that the common denominator is a cubed, and that's fine. That's a common denominator. I claim it's not the smallest common denominator. Because if you multiply this by a over a, then this becomes a over a squared plus 1 over a squared. And now you have the same denominator. So this is just a plus 1 over a squared. But if you want to go with the a cubed, nothing wrong with that. But observe what's going to happen. Here you're going to multiply by a squared. And here you're going to multiply by a. So you get a squared plus a over a cubed. And then you can factor out an a. And then you can cancel, leaving you with exactly what you had before. But there's going to be some extra steps of cancellation and so on. It's not the smallest common denominator. And what you started out with was the smallest common denominator. So you want to be careful. Questions? Bahara is not getting why we wrote b over x minus 1. Well, that's what the partial fraction decomposition is telling us to do. You look at the irreducible, it's x minus 1 of degree 1, so degree 1 less on top, degree 0, b over that, and you continue upping the powers until you come to the end, until you've exhausted the power. There is no easy way to solve, no. But if you've done 133, matrices. Use matrices. Yes, Jennifer is asking if the lowest common denominator will always be the denominator we started out with. The answer is yes. Can you elaborate why if we did not combine them, how the answer would be different? Well, if you had just x minus 1 times x minus 1 and you treated them as being different, then you would have a b over x minus 1, and then you would have a c over x minus 1. Again. And that's nowhere near the same as something over x minus 1 squared. You'd be missing the square, which may or may not play a role. Well, in fact, it will play a role. It will absolutely play a role. Nobody's working with polynomial matrices here. You would expand all of this and equate the coefficients, getting rid of all the x's. It's the coefficients that are important. Well, so people don't seem to understand how we would go about finishing that up. Why don't we, I don't know that we want to do it, but let's do it. So we would equate the numerators. Right, so all of this would be equal to the numerator we have. Now you would expand all of this or plug in values of x, your choice, whatever you want to do. We have two options here, but if you expanded everything, let's just think about what would happen here. Here you'll have an x squared times this, so you'll have ax to the 4 and other stuff. Here you'll have b times x times x times x squared. You'll have an x to the 4 plus other stuff. Here you'll have c times x cubed plus other stuff. And dx plus e times, this will give you an x squared, so x cubed and other stuff. And if you group, right, I mean, here you'll have ax to the 4 plus bx to the 4. And here you'll have a dx to the 4. So you'll have an a plus b plus d x to the 4, and then some other stuff. And that's going to be equal to x to the 4 plus x plus 1. And so the coefficient of x to the 4 on the left should be equal to the coefficient of x to the 4 on the right, and so on and so on. So you'll get 5 equations and 5 unknowns. and then you can solve. Yeah, doing these questions takes pages, absolutely. Pages and pages and pages of trivial algebra. Of just trivial algebra. So instead of integrating this huge business, you do a lot of algebra and then you get easier integrals. So it's it's give and take here. You're not getting easier integrals for free. There's a lot of algebra to be done, but it's just algebra. And of course, you don't just form the matrix with one line. It's because I'm lazy and I didn't want to multiply all of these things out. You can pretty much guarantee that you'll have one of these on the midterm. Exactly. As Jun Chen suggests, you'll do the same with x cubed, and the same with x squared, and the same with x, and the same with a constant, and you'll get 5 equations, 5 unknowns. Yeah, exactly that. All right. Is everything on web work 2 and 3 midterm content? It is. Absolutely. Quick matrix lesson. You don't need matrices. If you know matrices, you're certainly welcome to use them. What content will be on the midterm? Certainly everything we've done so far. Possibly more. I thought we would finish this partial fraction decomposition business today. I guess we haven't, but certainly expect it to be on the midterm. Consider this. Yeah, that's the thing. Matrices just makes everything neater. Slightly faster sometimes. Web works are meant to be both on the 24th for obvious reasons, right? Because it is midterm material. And the midterm is on the 25th, so yeah. We'll see. If we don't, we'll extend. But the beginning of web work 2, well, first of all, yeah, the beginning of web work 2 is really just use substitution. And my original plan was to open up web work 3 and not 2, but then I know what's going to happen. I'm going to get a ton of emails saying, is it normal that we have web work 3 and not web work 2? And yeah, so I didn't want to deal with that. All right. Consider this. You know what's going on here, right? Immediately you recognize that the numerator has higher degree, higher than or equal to the degree of the denominator. So long division is the first thing you want to do. Right? Because partial fraction decomposition does not apply if the numerator has the same or higher degree as the denominator. So let's do some partial fraction, some long division. This is x to the 6. And we ask the question, what must we multiply to x squared to get an x to the 6? And of course the answer is x to the 4. So that's x to the 6 minus 4x to the 4. This minus this is 0. This minus that is 4x to the 4. And we repeat, what must we multiply to x squared to get a 4x to the 4? And the answer is 4x squared. So that is 4x to the 4 minus 16x squared. This minus this is 0. This minus that, 16x squared. And we repeat, what must we multiply to x squared to get a 16x squared? And the answer is 16. And when you subtract, you get a remainder of 64. Not a remainder of 0, but a remainder of 64. In general, you would stop when the degree of the remainder is strictly less than the degree of the denominator or of the divisor. So what does this suggest? This tells us that x to the 6 over x squared minus 4 is equal to this business plus the remainder over the divisor. Well, I mean, first of all, it was 0x cubed, right? And we didn't bring down the 0x to the 5 either, because we noticed that everything, we were always dealing with even powers anyways. There are always lectures. Right, so again, right, I'm suggesting that this is equal to that. You can verify by rewriting everything over a common denominator, and you'll see that everything cancels and brings you back there. So you see the idea, right? If you were integrating this, you can instead integrate this. This is easy to integrate, easy, easy. And now you have this to integrate. And you know how to integrate that, right? You could make a secant substitution. This has the form x squared minus 4. So you could let x be 2 secant theta, do a trig substitution. But the numerator is of lesser degree than the denominator. So you could apply partial fractions to this. The denominator is non-irreducible, it's just a difference of squares. And so, right now these are degree 1 polynomials. So we search for degree 0 on top. Right, very easy. You know what to do. Blah, blah, blah there. And that's 4. So it's easy to see that A is, I want to say 16, and B is negative 16. Can you just read that off? I'll let you do it, right? But once you have a lot of experience with partial fraction decomposition, then you'll just see it happening. Let's do one more example. Well, I mean, I don't expect you to see it immediately, but you know what to do, right? We're going to put everything back over common denominator. X minus 2x plus 2. This is a times x plus 2 plus b times x minus 2. And now you can equate the numerators. And then here, good values of x does the trick, right? If x is 2, then this is 4a is equal to 64. So a is equal to 16. And if x is negative 2, this disappears. And you get negative 4b is equal to 64. And there it is. One last one. It's just asking us to decompose into partial fraction form, not solve the variables. First thing we want to ask is, are these irreducible? If we apply the quadratic formula, negative b plus or minus square root of b squared minus 4ac over 2a over 2a. So this is irreducible, right? You don't want the square root of a negative number. Similarly here, negative b plus or minus the square root of b squared minus 4ac over 2a, again, irreducible. How does this decompose? Yes, indeed, right? A and B would be interchanged if you had defined them differently. Absolutely. But the final answer is always the same. X squared minus 4 is 16 over x minus 2 minus 16 over x plus 2. Right? Because partial fraction decomposition is unique. So if you had defined this as b and that as a, then they would have been different. But in the end, your final answer is the same. First of all, observe this would have been a polynomial degree 4. Once you square it, times a polynomial degree 2 would give you a polynomial degree 6 versus 4 on top. So the numerator is of lesser degree. So we're fine to go ahead with partial fraction decomposition. Both of these quadratic polynomials are irreducible. We're done. We're done. We're just going to write out the form, right? Degree 2. So ax plus b over that. We've exhausted the power. Move on to the next irreducible, which is also degree 2. cx plus d over x squared plus 2, and ex plus f over x squared plus 2 all squared. We have now exhausted the power. There it is. You would want to rewrite everything over a common denominator and equate the numerators and solve for a, b, c, d, e, f. 6 equations, 6 unknowns, you're good to go. Oh, this is a 2 here. Power 2. How are we doing? Practice this, and then next time we'll see how everything relates back to integrals. I mean, of course, you understand exactly how everything relates back to integrals, right? Instead of integrating this difficult thing, you can just integrate all 3 of these things, which are slightly easier. Despite the despite the denominator being a degree 4, Paul, I'm not sure what you mean there. It is degree 4, that's right. Because we have exhausted the power, right? It used to be power 2, so we go all the way to power 2. Will powers of 2 always give you ax plus b? Irreducible. I mean, it's the irreducible polynomial, which is a quadratic. If that's what you mean, then yes. Why is it ex plus f instead of just 3? What 3? Why? What do you mean by 3? Oh, instead of just e. Instead of just e, the irreducible is a polynomial of degree 2. So we search for a polynomial of degree 1 less on top. Yes, you do. I need 2 web works at the same time. How are we doing? Questions? All right. Thank you all for coming, folks. You guys have a good weekend, and I will see you next week. Next week, we're going to do integrals related to this, and then maybe start on chapter 6. Area applications, really. Applications of integration. All right. You guys have a good one. I'll see you then.